Okay, this is a continuation of the video for 15.6 for Calc 3, triple integrals. The video was getting quite long, and I think what we covered in the first part is as much as we would get done in the class. I think in the calendar it happens to turn out to be on a Tuesday, so what I'm thinking is I'm just going to have everyone watch this second video here on the Wednesday to get a couple more examples worked out, and that'll help enable you to complete more of the homework problems. Okay, so what we're going to do for the rest is I'm just going to work problems that are similar to the homework problems. Okay, we're going to work problem 21, and I'm just going to tell you that for number 22 on homework, you can just do the setup only and definitely do not try to evaluate that. And then we're going to look at problem number 34 because 21 and 34 are similar to problems that are in the homework. Okay, so let's go ahead and take a look at these. Yeah, just a note for number 22, don't attempt to evaluate number 22. Okay, but what I'd like to do is try this problem. Find the volume of the solid that's enclosed by the cylinder x squared plus y squared equals 9, and the planes x plus y equals 5, and z equals 1, okay? All right, so we're just finding the volume. So the first thing is that means that we're not being given an integrand. In other words, we're not given, like, say, w is some function of x, y, z, so that when we do our triple integral, we have an f of x, y, z in here to integrate with x, y, z, or whatever it is we're doing for this, right? We don't have this. Instead, we just want the volume itself in the domain. So for that, we're just going to make the integrand 1. If we just integrate 1, then when we sum that all up, we're just finding the volume itself. All right, so we're going to do an integral with the integrand as 1. And I don't know for sure what we should do for the direction. Maybe, I don't know. Let's just sketch first, and then we'll make a decision about the order. So what's going on here in the domain? Well, we have a cylinder, and the cylinder is x squared plus y squared equals 9. So that cylinder would be, z is unspecified, so it goes forever in this direction, and the radius would be 3, right? So I have something like this, like a radius of 3 cylinder, if you want to think of it like that. But it goes forever. Okay, so it's like a radius of 3 cylinder. I didn't quite draw that right because it would be around it would definitely be around the axis here, so like that. Yeah, but continuing in the whole direction, something like that. Okay, so there's a cylinder. There's also a plane, y plus z equals 5, where x is not specified. So it's a plane that just goes in this direction, right? So maybe what I could do is say, if x was 0, what would the intersection of that plane be with the yz plane? Because if I were just to take this, I'll use red here for a second. If I were to take this and say, okay, z equals negative y plus 5, that means that if you started at z as 5 and did a slope of 1 line, that would be a curve of that, or a piece of that plane, right? And then that plane would extend forever in the x direction like this. All right, so there's a plane that's cutting this cylinder, right? So just with that, I'm going to try to make a sketch that's without all the kind of construction lines of what's happening here. Right? We have a cylinder shape, but if you have a plane that cuts a cylinder, it's going to cut it into an ellipse. There's going to be some kind of an elliptical shape like that on the top. And then the rest of it's going to form this. And then it says the other thing is we stop when z is 1. Right, so this doesn't go all the way down to the bottom here. In fact, let me back that off a little bit. This is going to stop when z equals 1. So when z equals 1, that would be something like this. So this is kind of floating above the xy plane a little bit. There's a slice of it cut off, but the rest of it is a circular cross-section cylinder. And we're trying to find the volume of that. So we're going to integrate over that region, just an integral of 1. Okay, I don't really think, again, I don't think it matters a lot in terms of the difficulty level of this, but because there's going to be some trickiness no matter how we go. So let's just pick a direction. Let's do z, y, x. I like that one sort of as a default. All right, so the z integral, well, we're going to, at first, we're going to ignore the z. So while we're doing the setup, maybe I should label this let me do this. Let's label that the inner integral, the double integral, or the out. Let's do this, the outside integral. We could maybe think of it that way. We're going to ignore the z and talk about the y, the xy. So let me make my sketch. Dx, x, y, y. All right, so imagine that you took this right here and you projected down so that it formed a shadow in the xy plane. I think hopefully you'll agree that the shadow would be a circle, right? It would be a circle down here in the xy plane. So just drawing it, it would be a circle. And since this is 9 here, the radius of that circle would be 3. We would be having to cover that entire region. Okay, so I'm going to cover that in some way. And let's see. So let's go, well, we're going to start by ignoring the inside. And we'll pick an ordering. Now, we decided to pick y then x, so we'll go with that. If we do y first, that means we go in this direction. So I'm going to have a starting boundary and an ending boundary. So what's the equation of this edge right here? Well, that edge would be this equation right here, x squared plus y squared equals 9. So if I want to solve that for y squared is 9 minus x squared, y equals plus or minus the square root of 9 minus x squared, right? All right, so the lower boundary is the negative version, negative square root of 9 minus x squared. And the upper boundary here is the positive version, 9 minus x squared. Okay, so it looks like I'm going to have my limits of integration go from y equals negative square root of 9 minus x squared to y equals positive 9 minus, or square root of 9 minus x squared. And then to cover the region in the x direction, right, we have to go from x's from negative 3 over here to 3. So we're going to go from negative 3 to 3. So there's the outer two parts of the integral. All right, let's go ahead and work on the inside one then. So for the inside one, now we know that we've got negative 3 to 3, negative square root of 9 minus x squared to square root of 9 minus x squared. And then we want an integral. We have to imagine that our person now in 3D is standing on the bottom of the surface here because the last direction is this way. So I'm putting a person standing on the bottom of that, and they're jumping up this way. So they're going to start at z equals 1, and they're going to end when they hit this surface here. Right? So that surface, well, how would we find that surface? Well, we know it's this right here. It's this plane y plus z equals 5. So if I need that to be expressed in terms of z, I think I could just solve this and get that this is, yeah, z is 5 minus y. So the limits of integration for the final step, or it's really the inner integral, is z has to start at 1 and end when we get to 5 minus y. Okay? All right. And then the integrand is just 1 because we're finding the volume, and we specified the order z, then y, then x. So there's the setup, and now we're ready to integrate. I have a feeling this is going to get kind of ugly, but let's start with the z. So we have integral from 1 to 5 minus y of just 1 dz. Right, so there is no variable here, so the integral is just, the antiderivative is just the variable z from 1 to 5 minus y, so we have 2 copies. We put 5 minus y in here and 1 here. And so that would just be 5 minus y minus 1, or 4 minus y, right? Okay. So then we would do the next integral out, and that one is going to be the y integral. So for y, we have integral from negative square root of 9 minus x squared to positive square root of 9 minus x squared. And we're going to be integrating 4 minus y, treating y as the variable. So now we have two terms, one's a constant and one isn't. So the antiderivative here would be 4y minus 1/2 y squared, evaluated from negative square root of 9 minus x squared to positive square root of 9 minus x squared. Okay, so that means we have to plug in two copies. We have 4 times something minus 1/2 times something squared. And then we have another copy, minus 4 times something minus 1/2 times something squared. And I'm going to change color to do the plug-in here. So we're plugging in square root of 9 minus x squared here. And then we're plugging negative square root of 9 minus x squared in here. Negative square root of 9 minus x squared. All right. If we're lucky, things will cancel. We'll see. So we've got 4 times the square root of 9 minus x squared. Let's see, the square and the square cancel, so we have negative 1/2 here, and then this is just 9 minus x squared. Then we have a negative and a negative, so that's positive 4 square root of 9 minus x squared, right? And then we've got a negative, negative. That's positive 1/2. Oh, no. Yeah, this is negative, negative. But this negative is going to go away because we're squaring this whole thing. So this is positive, but we have a negative, negative. So 1/2, and this is 9 minus x squared. Okay. So we did get some cancellation because this and this are the same but opposite signs. And so this would end up being 8. 4 and 4 together is a total of 8 square root of 9 minus x squared. All right, so unfortunately not that great. And then the final one is x. Let me go back to a black pen here. We're going from negative 3 to 3 with respect to x. Negative 3 to 3 of 8 square root of 9 minus x squared dx. All right, so that's not super easy. You can't do a u substitution because it would require having an x here. This is where I would use a table. Okay, so I've published in Schoology now a table. It's not on the Mr. Felling site, but it's in Schoology. If you go to the materials section at the top of the page below the answer key for all the odds, I put another thing there which has a multi-page. Basically, it's a scan of all of the integral and derivative tables and trig identities that are in the back of the calculus book. So if you trust me, you can look this up. And by table, this turns out to be equal to the antiderivative ends up being the 8's on the outside. You get x over 2 square root of 9 minus x squared plus 9 over 2 times the inverse sine of x over 3. And then you would evaluate that from negative 3 to 3, okay? Which means that you would have to let's see, what did I do here? In my, maybe I'll just leave it at that because we're going to have to, well, no, we can plug in. Let's do that. Let's plug in. So that means we have 8, and then I have to plug in something there, square root of 9 minus something squared, plus 9 has inverse sine of something over 3, right? And then I've got my other copy, which is minus, and then I've got something squared square root of 9 minus something squared plus 9 halves inverse sine of something over 3. But we would be plugging in 3 here and here and here, and negative 3 here and here and here. So carefully boiling this down, you end up getting, let's see, well, this is 9 minus 3 squared, which is 9, so this actually goes away. Same thing here. This term right here is 0, so this goes away. So we just end up with 8 times 9 over 2 times the inverse sine of 1 minus 8 times negative sign, so that's plus, because these cancel, of, oh, I'm sorry, I'm looking at the wrong thing there. Inverse sine of 1. This term goes away, but I would have minus, and then 8 times 9 over 2 of the inverse sine of negative 1. Okay. And actually, if you think about it, if you take an angle and you take another angle, the signs are exactly the same but opposite, right? Sine is what we call an odd function. So this right here is the same as the negative of the inverse sine of just positive 1. So these add, and you end up getting these change sign. So I actually have 8 times 9 divided by 2, but then 2 of them, so the 2's go away. I end up getting 72 times the inverse sine of 1, which if you plug that in a calculator, well, actually we can do that. Inverse sine of 1, we're saying what angle has a sine of 1? Well, that would be the angle pi over 2. So actually the inverse sine of 1 is pi over 2. So the final answer here is 36 pi. We can get an exact answer. All right. So there's other homework problems that are near problem number 21 that have similar structures. So you can look at the video here for a hint on that. And then I just have one more example I want to do. This is a problem that's similar in number to the homework problems that we're assigning. I want to take a look at problem number 34 in the textbook. And I'm just gonna, I'm not gonna do the writing, I'm just gonna analyze and show you what can happen when we don't have planes or cylinders, if we have more general surfaces. So let's say we have the figure in the problem. They actually gave a picture of this figure. It showed, and we want to show the region of integration for this integral right here, 0 to 1, 0 to 1 minus x squared, 0 to 1 minus x, of some integrand f of x, y, z, which is unspecified in the order y, z, x. And we want to rewrite this integral in the 5 other orders, okay? So what would that look like if we just wanted to change the order of integration? We don't know the integrand, doesn't matter, we'll just leave it as f of x, y, z. But this is more complicated because one of the surfaces is curved. Okay, so in the original, if you were to try to recreate what's going on here, right, we have xz, which means we're projecting into the xz plane. So if you imagine that you're projecting onto the xz plane, that's forming this region here. So this region here is the same as this region here if you draw it out this way, right? This curve out here, let me use a different color. This curve here is this edge right here, okay? And the way they chose was to do, let's see, to do z first, right? So that's this blue arrow. They're going in the z direction first. That's why they're going from z equals 0 here to z equals 1 minus x squared. So how did they get the 1 minus x squared? Well, because they're specifying that this surface is 1 minus x squared. So when y is 0, you're just right on that surface. Z is 1 minus x squared for all y's. So the curve here would be, we start at x is 0, and we end at 1 minus x squared. And then to cover in the x direction, then if you looked at the, well, on the graph here, they specified this was a 1, which means we're going from 0 to 1 in the x direction. All right. What's happening for the inner integral here is that we're moving in the y direction, right? So imagine that you put your person here and had them kind of going in this direction. Where would they hit their head? Well, they would start at y equals 0, which is why this is 0. And then they would end when they hit their head on this surface, which is specified as y equals 1 minus x. That's why this integral limit of integration is 1 minus x. Okay, so just recreating what happens so we can kind of get a picture so we can change it. So the first thing we can do is we can just keep y as the inside and reverse this order. Let's go x first, then y. If we do that, all we're doing is changing the arrow to this direction, which means we start at x equals 0, and we stop at this same curve, except solved for x. So if z is 1 minus x squared, then if you solve this for x, you get the square root of 1 minus z. So you would go from x is 0 to x is 1 square root of 1 minus z. And then to cover in the z direction, you would go from 0 to 1. Okay, on the inside, you would have to now imagine that well, it'd be the same thing. So we just reverse these, but you're still going in the y direction. So you're still going from y equals 0 here and hitting your head at y equals 1 minus x. So this would be the second ordering that just reverses the outer two, but keeps y as the inside direction. Okay, so they asked us to rewrite the integral in all the other orders. So another order we could go would be to pick z first, okay? So if we pick z first, that means we're projecting down onto the xy plane, shining down along the z direction, and that means that in the xy plane down here, the domain would look like that. It would be a rectangular area. And then we could decide between z and x which one to do first. So let's say that we decided to do between y and z. So we're picking z as the inner integral. Let's go with y first. So if we decided to go y first, then we're going in the y direction. Let me actually match colors here. So if I choose y first, I'm moving in the y direction. I'll draw a blue arrow there. That means we're starting here at y equals 0, and we're ending on this line, which would be y equals y-intercept of 1, slope of -1. So 1 minus x, or negative x plus 1. Right? So we would go from x is 0 to x is 1 minus x, or y is 1 minus x, sorry. And then we would cover in the in the x direction from 0 to 1. Now, how would we establish the inner boundary? Well, if we are leaving z as the inner integral, then imagine our person here jumping. They would start at the place z equals 0, and they would stop when they hit their head on this curved surface here, right? And that is z equals 1 minus x squared. So we can go ahead and express it that way, because while we're working on z, y and x have not yet been integrated. So it's okay to have this x squared in here as the limit of integration. So we would go from z equals 0 to z equals 1 minus x squared. And that completes the setup. The only difference we would do if we wanted to go z as the inner integral, but start with x instead. So if we wanted to start with x first, then let me switch to actually red as the color. If we start with x, we would be going in this direction first. So starting at x equals 0 and ending at this same thing but solved for x. So from 0 to 1 minus y, covering in the other direction from 0 to 1. And then the inner would still be the same on the three-dimensional dot drawing. You're starting at the xy plane and hitting your head on this single curved surface here. So not too bad to switch it to projection on the xy, which is equivalent to doing the inner integral in z. Okay, where things get tricky is if you try to make the last one, or the inner integral x. If you try to do that, it gets more complicated. Okay, so let's imagine this, where we wanted to do an ordering with x on the inside. Okay, so if we're doing something with x on the inside, then where would the region be that we would project? I'm going to use a different color here for this because I have green and yellow already being used. So we would be projecting in the x direction, jumping in the x direction, which means we would project down here onto the YZ plane. So the domain would be the YZ plane, okay? And I've got it sketched here, right? The problem is that if you jump on the YZ plane, so imagine that we're doing the jumping here, right? Where you hit your head depends upon where you are in the YZ plane. Because for part of the YZ plane, this curved surface is above that part, which I've colored in yellow here. But for other parts of the domain in the YZ plane, the green surface is where you hit your head. So that means to evaluate that way, which of course we wouldn't choose to do, we would actually have to have two separate integrals. One integral for where you hit your head on the green, and one where you hit your head on the yellow. Okay, so let's take one of those. Let's say that we wanted to evaluate hitting our head on the green. Okay, so if you imagine your person here, let me actually back off some of this. You imagine your person somewhere in this region, So when they jump, they hit their head here on this green part, okay? Then that means that since this surface is given as y equals 1 minus x, let's see, we're going to, yeah, that's going to establish the boundary, right? We're moving in the x direction, so x is going to stop at 1 minus y. So we're going to go from x equals 0 to x is 1 minus y. The reason why I'm establishing this is I'm trying to make sure and verify which one is which here. So this integral here is the one that's over the green area, okay? All right, so let's actually analyze that, right? In the domain, right, there would be some portion of that where we're below that surface. How do we determine that? Well, it all has to do with where these two surfaces, z equals 1 minus x and y equals 1 minus x are intersecting. Because they intersect in a curve, and that curve you can project also down here onto the domain. Okay, so this curve here, right? The way we find that is to find the intersection of the two surfaces in 3D. So if you have the surface y equals 1 minus x and z equals 1 minus x squared, we could say solve this for x and get x is 1 minus y, and then substitute that in for the x in the other surface. Z equals 1 minus y squared. When you expand that out, you end up, you can, because the x is eliminated, you can now write this as a curve where z is a function of y. So in fact, this curve here, let me actually use a different color to highlight it. This curve here that I'm using in blue here, this curve is z equals 2y minus y squared, okay? So anything below this or in this region is gonna top out at the green surface, and anything in this upper left region is going to hit the yellow part, okay? All right, so let's work on the green one first. So for the green one, we could pick, let's decide to go z first, for example. So if I wanted to go z first, I'll use blue here. If I wanted to go z first, I would have to cover this green region only with a blue arrow, okay? Starting at z equals 0 and ending at z equals 2y minus y squared, the projection of the surface intersection down on that yz plane. That's why we have this integral limit of integration from 0 to 2y minus y squared. And then in the other direction, we just have to cover y's from 0 to and 1. And in the original problem, the boundaries were given as 0 and 1 here, okay? And then to finish it out on the inside, right, the inner integral would be we would start at x equals 0, and we would stop when we hit our head on the green surface, which is x is 1 minus y. Same surface, but solve for x. That's why this is 1 minus y here, okay? Then we would have to add that to the portion where we are topping out on the yellow. So for the yellow, if we wanted to do z first for the outer two integrals, we would be starting at this curve, 2y minus y squared, and then ending when we got to z equals 1. And then covering the other direction from 0 to 1. And then finally the inside would be the yellow surface. So we would have a person standing over here, jumping up and hitting their head here. So if z is 1 minus x squared, if you solve that for x, because for the inner integral we have to have x, that ends up being x is the square root of 1 minus z. So that's why we got this as the inside integration. And we would then have to sum the contributions from each of those two regions. Very, very complicated, right? There's one other ordering, and it's basically the same as this, except with the y and the z reversed. So did I do that one on this page? Yeah. Okay, so if we went through the same thing, we would have the same boundaries here, right? The same ceilings. The difference is we would be using y first, so we would be, like, let's do this over here for the green one. We would be using the red arrow, and that means we would start at this boundary, which is z is 2y minus y squared, but we'd have to solve it for y. We would go from y equals 1 minus the square root of 1 minus z up to y equals 1, right? And then cover from 0 to 1 in the other direction, in this case z, right? The ceiling would still be since we're going in the x direction, from x equals 0 to x equals 1 minus y, the green surface. And then over here, we would be covering the yellow portion of the domain in the yz plane. We would start at y equals 0, right, and end when we got to that y equals 1 minus the square root of 1 minus c. Okay, and then covering in the z direction, we would go from 0 to 1. Okay. And then the ceiling would be the same as the last problem. All right, so clearly some orderings are much harder to integrate than others. All right, so I think there's a problem similar to that, to 34. So using that, hopefully you can at least attempt the problems in the homework. On Thursday, we're just going to answer questions, and I imagine we'll have plenty before we move on Friday to talking about cylindrical coordinates, which is a simplifying method when you have cross sections that are circular. All right, that's it for part 2 of the 15.6 video.